Hi everyone, this is Professor Iris Miano giving you your week 6, day 10, if I'm not mistaken, lecture video on proving lines parallel and the angles of a triangle. So in starting off in section 4.3 here on proving lines parallel, we are going to be introducing even more theorems, but they're going to be very familiar to us in their wording because you're going to find that they are if I'm not mistaken, the converse of a lot of the theorems that were presented in section 4.1. So you'll read these and you'll be like, didn't we already cover these? Yes, kind of, but you know, the switcheroo according to the converse. So that means that these relationships that are being described by the theorems, you know, in 4.1 section and 4.3 that are connected via, you know, this converse relationship, that means that these concepts are biconditional, right? They go in both directions, but they are presented as separate theorems in order to really highlight the fact that you could go in either direction with it. Alternatively, these theorems could have been worded with phrasing if and only if in lieu of being a strict conditional of the if-then variety. Okay, so that being said, without further ado, let's go ahead and read through all of these theorems that are presented in section 4.3. And as you can see here with the numbering, this is the first theorem presented in this section, and it states if two lines are cut by a transversal so that corresponding angles are congruent, then the lines are parallel. So let's entertain this case where we have lines M and N cut by transversal line L, as you see in the figure here, and then two corresponding angles are presented, angles 1 and 2. If indeed these angles can be found to be congruent to each other, then you can claim that the lines M and N that were cut by the transversal must have been parallel in the first place, okay? So if two lines are cut by a transversal such that alternate interior angles are congruent, then the lines are parallel. So basically, what you're going to find with most of the initial theorems in this section is that there are different ways of being able to arrive at a conclusion that some lines are parallel. So we saw in the previous theorem, the very first theorem, that if you've got two lines cut by a transversal such that the corresponding angles are congruent, then you can claim that the lines are parallel. So it's like the congruency of the corresponding angles needs to be established first, and then parallelness can be established. Like it's in that order with these theorems, whereas we had the opposite order happening with the theorems presented that have similar wording in section 4.1, just to be clear. Okay, so here's the second theorem in section 4.2. We have two lines being cut by a transversal again, and if alternate interior angles, much like the one seen in the figure with angles 1 and 2 are congruent, then again, that's another way that you can claim that the two lines being cut by that transversal, M and N in this particular illustration, are parallel. All right. How else can we prove lines parallel? Well, you can have alternate exterior angles congruent to each other. If you find this to be true, this is another way you can conclude parallelness, okay? And you can also do so with certain specific angles being supplementary to each other. Here's two lines being cut by a transversal such that the same side interior angles are supplementary. If that's the case, then lines M and N must have been parallel in the first place. Okay, cool. Also true for same side exterior angles, as indicated by these angles 1 and 2. If they're supplementary to each other, you can claim lines M and N are parallel. Okay. Cool. Now we're going to mix it up a little bit. This sixth theorem in section 4.3 is a little bit of a deviation. It's got its own distinct wording compared to what was happening with the first 5. They were merely the converse of a lot of theorems that were presented in section 4.1. But this theorem is very distinct, and it is conjuring up a scenario that was actually kind of illustrated in an example that was presented in a previous lecture video. So if you recall, there was a partially completed proof with 3 lines and a transversal, and there were several interior, there were some interior and exterior angles that were being considered, and we wanted to link up an angle 1 and angle 4, if memory serves me correctly. Anyway, the ultimate thing that would have made that proof run a little bit shorter in its write-up would have been the incorporation of this just now presented theorem, which is basically illustrating the transitive nature of being parallel. So the theorem states, if 2 lines are each parallel to a third line, then these lines are parallel to each other. So in this case, if we're linking this figure with the concept of this theorem, let's say that we are given that lines M and R are parallel, and similarly but distinct, lines N and R are parallel as well. So notice that lines M and N are both parallel to R, so that means that they must be parallel to each other by virtue of this theorem. So yes, the relation of being parallel is now, as far as our work is concerned, we can consider this to be transitive. This relation of being parallel has the transitive property, is what we can now claim. All right, I will in a separate video demonstrate construction 7, which is how to construct parallel lines. It's probably the most complex individual construction that I demonstrate, so definitely be prepared to put your thinking cap on, or whatever silly thing we want to say for that. I just want to give you a heads up that it's a little bit more involved than some of the other constructions that we've seen. So stay tuned for another separate video that we go over that. Okay, so in general, there is a strategy for writing proofs in this section that the book offers, and I think it's a good thing to keep in mind as we enter into the homework exercises, and it's to establish a condition found in one of the theorems. So what does that mean? Well, let's at least go through a whole example of writing a proof together in this section, and hopefully we'll be able to see what is meant by that. So notice that you are given that there's a couple of pairs of congruent angles, and also you're given this figure. One thing that I want to highlight about this figure that's relatively new, maybe, is the incorporation of these arcs. So please note that the interior of angle 1 and angle 3 has a single arc inside of it. Now that is notation that is often added to figures to indicate that angles 1 and 3 are a congruent pair. So this information right here, angle 1 is congruent to angle 3, is also inherent in this single arc inside of the interior. Notice that distinctly from that, but similarly, angles 2 and 4 have 2 arcs in their interior. That matches them up as a distinct pair of congruent angles as indicated by the given information. So there's now more notation associated with figures that are going to match up angles as being congruent for us now, okay? So we want to take that information, the congruency of angles, everything that we can surmise from this figure, and we want to reason our way all the way through to being able to claim that line CD is parallel to line EF. That's how you read this proof statement here. Okay? So, and even though there are no points explicitly shown on this figure, and that's exactly how it is in the book as well, we want to note that there are, points that are having these capital letter labels, okay? So that way we can have a mechanism by which we can name any angle that's produced here. So for instance, if we wanted to name this angle that I'm hovering over with my cursor, that would be angle AJC. See what I mean? Whereas this interior angle, which we could call AJG, angle AJG could also be called angle 1. So some angles have shorter names with the numbers involved, and other angles, if we needed to name them, we would use the 3-letter code indicated by the, the vertices in play. Okay, cool. So, always, you will want to start with the given information. Now, some folks would for whatever reason, split up these two bits of given information into separate statements. My rule of thumb is just throw it all in the first statement. The first statement can be multiple statements as long as they are justified with the same, reasoning. They're given. So plop them all in, say that it's given. The first step is always a freebie for you, and it's always the same. It's always just place at least one component of the given information in that first statement and justify it with the word given. Done. Now, where do we want to go from there? Well, let's see. I go ahead and change these congruency statements to measurement statements, okay? Now, why would I want to do that? Because it looks like later on I'm going to try to make some sort of angle addition postulate thing happen. And if you look carefully at the wording of the angle addition postulate, you need to have everything in terms of measures being added together to be equal to a collective measure. So this change in notation is warranted according to the pathway that I see myself heading down in order to write up this proof. Like eventually I'm going to be able to match up angle AJD as congruent to angle JKF. Spoiler alert, that's what's happening. And they are congruent, or if I can match them up as congruent, they're corresponding. And if you have lines that are being cut by a transversal such that corresponding angles are congruent, that was the very first theorem presented in this section, then you're going to be able to claim that those lines are parallel, which is what I'm heading towards. And of course, hopefully it's terribly clear, the justification here using definition of congruent angles is perfectly fine, because congruent angles are angles that have equal measures. And if you're uncomfortable with saying definition of, if you just want to make sure you're using the definition correctly, it's always a good idea to just actually write down the definition. However, if you're using the term correctly in your justification, if it is good justification to use the definition of that term, simply stating definition of is perfectly acceptable, as you can see that I've done here. Okay, now next, yes, I'm going to use where am I going with this? Let's see. What I did is I took the first equation in my second statement and I added the measure of angle 2 to both sides. Check this out. Okay, cool. It's totally fine for me to do that because I'm using the addition property of equality, or APO, if you want to shorten it up. It might not feel intuitive to do that. Like, why would you think to do that? Experience. I don't know. I've been doing this stuff for a long time. So if it's not clear where we're going with this, just stick with me, okay? It looks like I would assume in the next step we would probably replace this measure of angle 2 with measure of angle 4, and then we're going to get something legit to spring off from there in order to eventually get to these collective angles being congruent. Okay, but let's just see. Yes, that's what I was thinking. So from statement 3 to statement 4, please notice the only difference is that this measure of angle 2 on the right hand side of the equation turned into a measure of angle 4, and it's cool because in statement 2 the latter, the second equation, linked those two values up as being equal. And you could always, anytime two things are equal, you can always directly replace one thing for another, and that is substitution. Moving on, what else do I do? Here's where angle addition postulate, or AAP if you want to shorten it, perfectly acceptable, comes into play, where I am taking the measure of angle 1 plus the measure of angle 2 and calling it equal to the measure of angle AJD. I believe I alluded to that earlier, right? We have a main angle here, and it is the sum of the two, adjacent interior angles. Same with angle JKF being the collective measure of angles 3 and 4. Okay, and then, so once I have that in play, it looks like I'm going to substitute that again. So take what you have in statement 4 and use the equalities that are illustrated in statement 5 to create statement 6. By that I mean measure of angle 1 plus measure of angle 2 can be replaced by the measure of angle AJD, right, by virtue of the first equation in statement 5. Similarly, the measure of angle 3 plus the measure of angle 4 is equal to the measure of angle JKF, so a direct replacement can happen there as well. So this is substitution technically twice over, but it's still the same justification for those one could argue two separate moves that are happening. All right, now when measures are equal, angles are congruent. Again, I am using the definition of congruent angles, just in the reverse direction from what I did to justify statement 2, but that's fine. Definitions are reversible, so the biconditional nature of it is inherent in the fact that I am using the definition of a term. Now that I have these particular angles, AJD and JKF, congruent to each other, I can notice that they are in corresponding position to one another in regard to the two lines being cut by a transversal. So therefore, I can make my proof statement happen by stating that very first theorem in this section. Okay. If two lines are cut by a transversal so that the corresponding angles are congruent, then these lines are parallel. So this is me just cutting and pasting the exact verbiage of the given theorem, but it can be acceptable, to slightly reword the theorems. Truncating some words is okay. Using symbols instead of some words just to make it even more concise is acceptable. As long as you are not missing in your presentation of the theorem that's supposed to be justifying some step in a proof, as long as your retelling of that theorem isn't missing vital information, then it's perfectly fine to reword these theorems with a more, like a less stuffy vernacular, I guess I would say. So feel free to do that, and if you have any reservations about whether or not your rewording is enough or sufficient as an alternative way to describe the concept associated with the theorem you want to use, run it by me, and I would love to just either confirm or deny that it's a good rewording. All right, and with that, so let me go back one thing there. That's a wrap on 4.3. Let's go ahead and enter into 4.4, in which we get pretty deep, like I would say elbow deep, in some triangles. We're going to discuss like pretty much every single kind of triangle that's possible. They're going to be defined for us, and we're going to have a theorem associated with the interior angle measure sum of every single triangle ever, and that's going to help us prove some related theorems that are called corollaries. So we'll get all into that in just a moment, but first let's go ahead and formally define what a triangle is. It's the union of three line segments that are determined by three non-collinear points. So remember what the word collinear means? It means that it's three or more points that lie in line with one another, possibly on a line, but that's not necessary. Now, if 3 points are non-collinear, then that means they can't lie on a line. So here is an example of 3 such points. These points A, B, and C are non-collinear, and if you draw line segments that connect all of them, you have created a triangle, okay? So there you have it. And remember, there's no wrong way to name a triangle. If you just take the 3 letters that are the names of the vertices of your triangle, and any combination with a triangle symbol in front of it, that's the triangle's name. We'll get into some specifics later on with what we do with triangles in some sections involving proving that they're congruent to one another or similar to one another, in which case we will want to be careful about naming our triangles so that the vertices that correspond between the triangles in the congruency discussion line up with one another. Anyway, but that's a whole nother ball game. We'll get to that a little later. Let's go ahead and draw some fun, beautiful triangles. So what I recommend that you do is grab your straight edge if it's within reach, and that's anything that has a straight edge to it. You just want to, for fun and for completeness and to have a good structure to what you're doing here, you want to draw your triangles as beautifully as you possibly can in your notes, if indeed you are taking notes. So here we go. Let's go ahead and classify all the different kinds of triangles, starting with the ones by sides. So what's a scalene triangle? It is a triangle whose 3 sides are not congruent to each other at all. So you might notice this what I call tick mark notation that's going on here. This, what appears to be the shortest side, has one tick mark, and then another, probably the medium length side among the three sides, has two tick marks, and the longest side has three tick marks. Now, the length of the side doesn't have anything to do with the tick marks. What you want to note with this is that a one tick mark length side is not the same length as a two tick mark or a three tick mark. So the number of tick marks indicate a distinct length with the side. And so this notation will lend itself to matching up congruent sides when you see the next two types of triangles. Okay, so a scalene is a triangle in which none of the three sides are congruent to one another. Okay, and that's what these distinct tick mark quantities are indicating. Okay, now on the other hand, let's go back. An isosceles triangle is a triangle that has two congruent sides. So notice that we have what's commonly called the base edge with one tick mark, and then the two, we call them, what do we call these edges? The congruent edges, what do we call them? I guess we just call them the congruent edges. I feel like they have the legs. I'm not sure. It's hilarious that I'm like rambling about like what the edges are called here when I should just know this off the top of my head. LOL. Let's see if I can flip to it real quick in the book. Hold up. Just a moment. Stick with me, guys. Oh, too far. Yes, keep going. No, it just says number of congruent sides. It does not define it as any kind of particular. Well, later on we're going to have a section completely dedicated to, or not completely dedicated to, but we talk a little bit more detail about isosceles triangles. Like there's more to it than what we talk about in just this section of chapter 4. In chapter 5 we'll have like, oh, actually, yes, in 5.3 we have a whole section on isosceles triangles coming up. Okay, anyway, so, you know, these are the congruent edges, and then there's a base edge. That's the non-congruent edge. And so even though it's not part of the definition, I think it really warrants at this point thinking about isosceles triangles as having congruent base angles. Now these are the angles that are formed when the base meets one of the congruent edges. So there's one right here, and then here's the base meeting the other congruent edge, and it's indicated with two arcs here. So the base angles are always congruent to each other, and it's because also they have this relationship as being opposite of two side lengths that are congruent to each other within the triangle. Okay, that's a lot of information, and more than you actually like technically need to get through this section, but things are coming up very quickly that are going to be relevant to isosceles triangles, so I thought we would just kind of get a few things squared away now. Lastly, if all three edges are congruent to each other, we have what's called an equilateral triangle. This one, yeah, so notice the tick mark notation here. Each of the three edges has exactly one tick mark, and that means that they're all the same length and therefore congruent to each other. Okay, we can also categorize triangles in terms of the relationships involved in their interior angles, and the first one that is going to be defined is acute. Yes, we have used this word to describe simply the measure range of an angle. If you recall, acute angles are angles that measure between 0 and 90 degrees. Well, that happens to be the case with all of the interior angles in an acute triangle. So notice that I have a representative figure here. Angle ABC is acute because the measure of angle A, the measure of angle B, the measure of angle C are all less than 90 degrees. So that's what makes it acute. An obtuse triangle, you might easily, erroneously assume that it is, by context clues with the definition of an acute triangle, you might assume that an obtuse triangle is a triangle that has all three of the interior angles as being obtuse. But what we're going to find with the very first, the theorem that's presented in this section is that that's actually impossible because the interior angle sum of any triangle's angles has to be less than 180 degrees. So if you had even two angles being obtuse, you would, not be able to have the figure be a closed polygon triangle, right? Okay, anyway, so for this particular type of triangle, you have it categorized as obtuse if you have one of the interior angles as obtuse, and the other two must be acute, okay? And again, that's just because we do not have enough degrees to go around in order for two interior angles to be obtuse at the same time within a triangle. So we'll get into more detail about that in just a little bit when we get to the theorem and corresponding corollaries. Now, a right triangle is probably something that everyone's super familiar with, but just in case, let's define it formally as a triangle in which exactly one of the angles is 90 degrees, and therefore the other two angles have to be acute, okay? And in particular for this figure, the right angle in question is the one inside of the interior B, as indicated by this little box. And lastly, we have equiangular triangles, which are also equilateral, okay? But if it's defined as an equiangular, then the thing that we care about in describing this triangle is to say that the interior angle measures of all three of the triangles are the same, and therefore they have to be a particular measurement. We actually have a corollary alluding to that concept that's going to be presented shortly. Okay, now I think we're ready to talk about this theorem that I've been going on and on about. Yes, we are. So here is the first theorem. In fact, I think it's the only theorem. All of the rest of the theorem-like statements that are presented are actually technically called corollaries, and they're connected to this theorem. They're direct, what's the word I'm looking for? Direct results of this theorem. This is like the theorem, and the corollaries are like sub-theorems to it. It states that in a triangle, the sum of the measures of the interior angles is 180 degrees. Now, your textbook has a little bit of an illustration that describes like the physical proof that anyone can entertain in order to convince yourselves that this is going to be the case. So if you were to construct any type of triangle, and by construct I mean cut a triangle like out of paper or something, or any kind of a material that easily rips, and if you ripped off all three of the angles and lined them up to one another, you would find that their collective measure would be 180 degrees, or you could say that the three angles are supplementary to one another. I'm not sure if supplementary can be attributed to collections of angles. I think it can be, and if that's the case, then we would say that they sum to 180 degrees in their measures, so that's why I would think that using that term would be appropriate. In any event, they form a straight angle, right, when they're all laid down together. So that means that every triangle that you could come up with, as long as it's a legit triangle, the interior angle sum is strictly 180 degrees, and we can use that information to calculate some things involving triangles, okay? So yeah, this is definitely a very important restriction bit of information associated with triangles that's going to become very useful for us in a myriad different contexts later on. Okay. Let's jump right into these corollaries. Like I said, corollaries are more or less like sub-theorems. They're always connected to a main theorem, which was the one that we just saw about the interior angle summing to 180 degrees. So you always use that main theorem information in order to reason through your way for any connected corollary. And so what I will do for all of the corollaries, I will at least give you a line of reasoning, not perhaps with justification in a chart-like manner, but I'll give you some guidance on how you would prove them. And for one particular corollary in this lecture, I will go through the formal proof of it with you. So, but in any event, let's go ahead and for corollary 4.4.2. So this is the second, theorem. in section 4.4, it states each angle of an equiangular triangle measures 60 degrees. Okay, let's entertain this idea with a particular triangle ABC, and let's assume that it's equiangular. So notice that we have a single arc in the interior of all of those angles, which is to say this right here. The measure of angle A equals the measure of angle B equals the measure of angle C. Furthermore, just by virtue of being a triangle, we know that this is true. This is the result of the first theorem that was presented in this section. The interior angle sum is 180 degrees for triangles in general. So if you marry this information together and make some substitution happen, right? If the measure of angle A is equal to B, you can replace it. You can transitive property your way into saying that the measure of angle A is also equal to the measure of angle C. You can substitute it there as well. Combine like terms, division property of equality, and therefore you have it. Measure of angle A, and therefore all of the rest of the angle measures has to be 60 degrees as indicated by this corollary. All right, so again, what I'm presenting with you here with these steps is a line of reasoning that one could use in order to write up a formal proof of this corollary. But this, however, is not a formal proof because it doesn't contain justifications in like any kind of organized format, which the standard organized format for us at the moment is the chart-like mechanism. Okay. Cool. Let's, oh, look at this. Sorry, let me just make an extra statement there, formally tying the measures of all of the interior angles to the 60-degree measurement. Okay, there you have it. So, moving on to the next theorem, which is a corollary 443. The acute angles of a right triangle are complementary. Cool. Give yourselves a right triangle, and what can you definitively deduce about this triangle? Two things. Well, it's a triangle, right? The measure of the angles sum to 180 degrees. What do you know about the measure of angle B? It's 90 degrees. So you can make a little substitution right there and then ESPO your way into saying that the measure of angle A plus the measure of angle C, the two, acute angles that are left, sum to 90 degrees. Well, what do you call angles that have measures that sum to 90 degrees? You call them complementary. So here's a line of reasoning that could get you through proving this corollary here. Again, it is not a full formal proof, though. It could help you write a full formal proof, though. All right, moving on. Next corollary, if two angles of one triangle are congruent to two angles of another triangle, then the third angles are also congruent. This is the one I'm going to formally prove for you, okay? So here's the exercise. We're going to write a formal proof of this corollary, and we're going to use these two figures right here, which I believe are on your page. And also, I want to say that the next page in your lecture notes is where the formal proof of the corollary starts, or where you have like room to write. So, and I want to say, if memory serves me, that the given and prove statements are blank, so it's our job to use the figure and the wording of the corollary in order to write the given and the proof statement. So I'll go ahead and just click forward and show it to you. I would say that, okay, and also let's refer back to this. If two angles of one triangle are congruent to two angles of another triangle, so then we need to say what? We have these two triangles A, B, C, and D, E, F if we're trying to link that to the figure. And we need to formally state which angles are congruent pairs, and the single and double arc notation in the figure is what's allowing us to link up the corresponding congruent angles. That's angles A and D are congruent because they each have one arc in their interiors, while angles B and E are another congruent pair by virtue of the same, conclusion. So what we're trying to prove here is the consequent, right, or the conclusion of the conditional statement. The third angles are also congruent, the third angles being angles C and F. That's what we're trying to arrive at by virtue of writing this proof. So always start off with your given information, plop it into the first statement, and reason it with the justification of given. Cool, done deal. And then where can we go with this? Well, we can say that by virtue of these two polygons being triangles, their interior angle measurements equal 180 degrees. And that's that first theorem. So the sum of the interior angle measures of a triangle is 180 degrees. Boom. I just went ahead and wrote the entirety of that theorem as justification for this first move that I made after the given information was laid out. Okay. Then it might behoove me to formally show that these angle measures for these congruent angles are equal to each other. So congruent angles have equal measure. Here's me being careful and not just writing definition of congruent angles, which would be a perfectly acceptable alternative justification there. Okay, and then I think I'm probably going to do a little bit of substitution. What do I do? Yes, or no, sorry, transitive property technically, but anytime you're using the transitive property as justification, it could be argued that substitution is a perfectly acceptable alternative justification. But yes, transitive property is here. So just to be clear, I am taking the two equations that are given in the second statement and noticing that they're both equal to the same thing, the 180 degrees. So therefore, the 180 degrees is acting as like a middleman linking together these interior angle sums. So that's how I am using the transitive property to make the claim in the fourth statement. Okay, now I'm ready to link the fourth statement up with the third statement and do some substitutions. So if I'm not mistaken, I think on this side, I'll probably replace the measure of angle A with the measure of angle D, and similarly for B and E. Let's see what I did there. Yes, I was thinking that way when I wrote this up. So cool, this is just substitution because it's established in the third statement that these measures are equal. So I'm gonna replace them in the fourth statement to make my fifth statement. And I'm doing this because I eventually want to, subtract these equal things on both sides of the equation, which I will do just now, and with using subtraction property of equality, which I'm acronyming with SPO or SPO, however you like to say it. And then look at these angles. They're equal in measure. That also means that they're congruent. Again, using the definition of congruent angles, rewritten in kind of the reverse way as stated previously. And that's a wrap. I have linked up those third angles, C and F, through congruency, which is exactly what I was trying to prove. So this proof is finished. Okay, so let me know if there's anything we can elaborate on in class. Let's present one last corollary. And again, we're not going to do a formal proof of this one, but I'll give you a line of reasoning. And the corollary states the measure of an exterior angle of a triangle equals the sum of the measures of the two non-adjacent interior angles. Whew, a lot of words there, kind of a word salad. So let's go ahead and refer to a specific example figure to try and, reason this all the way out. So here is some triangle ABC with the line segment BC extended so that we can present an exterior angle, which we're calling angle 1, okay? So the thing that we want to say is true here is that, by virtue of ABC being a triangle, we could say that the sum of their interior angles is 180 degrees. Furthermore, angle 1 and angle A, which is the interior angle here that I am showing with my cursor, if I sum them together, they should be equal to 180 degrees as well. How do I know that? Well, because they are forming a straight angle when they're adjacent to each other, and together they form a straight angle. So that means that they must be supplementary. Their angle sum is 180 degrees. A couple different ways that you can describe that. It most behooves us to come up with this equation because I'm about to link these two equations up together since they're both equal to 180 degrees. So that means the measure of angle 1 plus the measure of angle A must be equal to the interior angle sum of angles A, B, and C. So that's what I have here. Notice that I have the same value of the measure of angle A on both sides of the equation, so I'm going to SPO my way into, canceling them out on both sides. And here we have it. This is actually the result that I was trying to get at. The exterior angle is the sum of the two non-adjacent interior angles, which are B and C in this specific case. Okay? Sorry, let me go ahead and let you guys see that for another second. Or you can, you can always pause the video at any point and go back to things if I ever go too fast. And that's a wrap. for today. So here are these suggested homework problems from these two sections that were just covered in this lecture video. If anything in the lecture video or homework is unclear, let's talk about it in class. I'll be delighted to show you anything, answer your questions, demonstrate problems to your heart's content and whatever it is you want to see. Okay, I look forward to seeing you soon.